All right, so what we're going to be focusing on today is assignment problems. All right, now again, like critical path stuff, it's very long, but it's also very useful. Okay, so what we're going to start off with is called bipartite graphs, which means what the definition for a graph like this is basically a network, right, where you can divide the vertices into two groups such that no two vertices of those groups within a group are connected. Okay, or another way that I used to think about these graphs, right, is something like this. If I have a graph like this, then what I used to think was I can color each of these graphs in a separate color, right? I can color this yellow, this one green, this one yellow again, and this one green, and this one yellow. And as long as I don't have any yellow connected to a yellow, right? If I don't have something like this, as long as I don't get that, then the graph is bipartite, and here I've represented by the groups by colors. All right, so essentially the point is that if I can divide it into two groups where the vertices are not connected of any, like within that group, then that graph is bipartite. That's the definition. All right, and we'll talk about where it's useful in just a second. Right, so now that you know what a bipartite graph is, we're going to look at how it's actually useful for us. Okay, so what we can do is it can be used in places where you have to divide people into groups. All right, obviously two groups. So for example, right, you have a bunch of children and they want to play a bunch of sports. Okay, so let's say that where you work, right, it offers some tennis, all right, soccer or basketball. These are the sports you offer. All right, so these are the sports your club or whatever offers. And let's say you have a bunch of kids, right? You have A, who wants to play either tennis or soccer. All right, you have, actually I'll use a different color for that. All right, you have B, who wants to play either tennis or basketball. All right, you have C, who wants to play soccer, all right, and only soccer. You have D, who wants to play. What I'm going to do is I'm going to add in another sport. Let's say cricket. Okay, and D, who wants to play either cricket. Whoops, wrong color. Either cricket or basketball. All right. So my question to you is, how can you divide the children into groups such that each of them get at least one of their preferences? So the way to go about it, right, is to find the kid or whatever with the least preferences. All right, in this case it's C. He has only one preference, so we give him soccer. All right, next, if we give him soccer, right, then A has to be playing tennis. Okay, assuming you can only assign one kid to each sport. All right, because he can't do soccer anymore. So therefore B has to be doing basketball, and then D has to be doing cricket. So like that, we have created a network here where everybody has got a preference that they wanted to play. That's where these sort of graphs come in handy. All right, now this is just a situation where it's based on preference, right? But sometimes people may not get their preference. All right, sometimes we just have to rely on getting something that's close enough. That's the best case scenario, right? And the way you do this is you take your information, all right, and you add weights to it, essentially. Right, so what you do is you assign weights to the graphs. So for example, if I come back to this one, all right, and I assign weights to the graphs, all right, I make it like some not possible one, All right, I'll add this in so that is so we can't make it up, right? So let's say everything is close to as it was before. Whoopsies. Okay, so let's say something like this. I don't know. I think it's still possible to do it, but the point is that let's say it's not. All right, let's say we can't find a solution to it. What we're going to do is we're going to add weights to it. Right? How much does he want it? How much does he prefer it? All right. This weight doesn't necessarily need to mean how much. It could just mean something different. Like it could be like how good you are at that sport, or what position you got in that sport, something like that. All right, just some weight to it. So let's just add some random numbers. All right. Okay. So we've added weights to these graphs. Now, it's still a bit complicated as to what's happening, right? But what we can do now is write this as a matrix. Now, we obviously remember how matrices work in these sort of scenarios is that we can have A, B, C, and D, all right? And we can have tennis, soccer, basketball, and cricket, right? And we can write in, like fill in the stuff based on that information, right? So we can say that A has a preference of, well, like whatever it is, how good he is at tennis is 1. He's 3 score points good at soccer, all right? And the rest is 0. Okay, and you go ahead and just quickly fill that in. I'll try to do this as fast as I can. 5-7 cricket, and he wants to play soccer only. Okay, I think that's it. All right, so now that I have this matrix up, what I can do is use the Hungarian algorithm. Okay, so the Hungarian algorithm is this, all right? In each row, subtract the minimum value. So in each row, find the minimum value, subtract that from all values. Okay, next, do that for the columns. So in each column, find the smallest and subtract. Next, what we're going to do is we're going to cover the zeros of the matrix. All right, so we're going to find the zeros and we're going to cover them using the minimum number of horizontal and vertical lines. So what that means is it will be a bit more clear when I do it in an example, right? So cover, all the zeros. Okay, so if this number of lines that you found here is equal to the number of rows, what we're going to do is we're going to get to this step, all right? And if they're not, we're going to do this step. So if they're not equal to the number of rows, we find the maximum uncovered number. All right? And subtract this value from all the uncovered numbers. We find the minimum uncovered number. That's on me. We find the minimum uncovered number and subtract this value from all uncovered numbers. All right. And add this value to the numbers covered by 2 lines. All right, again, it might seem a bit, I don't know what she's talking about right now, but give it a moment. I'll explain it and then it'll be a bit I'll do an example and then it'll be a bit more clear. And then what you do is you come back to this step. Okay, now let's say the number of lines you found is equal to the number of rows. What you do is find the pattern of zeros all right, such that the number, such that each row and column has exactly 1 0. All right, and what you do is apply this pattern to the original matrix to get the optimal solution. All right, so we'll go through it now, and hopefully it will make a little bit more sense. Now, we find the smallest value in each of the rows. In this case, it's 0, so nothing really changes. Same for the columns. All right. Now we try and cover all the zeros with the minimum number of lines. Now, what that means is we can either draw horizontal lines or vertical lines, and we want to cover all the zeros in the minimum number of lines. All right. So, to do that, all right, let's go ahead and start trying. So what we can do is we need to cover this 0, right? Obviously, we need to cover all zeros. So to cover this 0, we can either draw a vertical line or a horizontal line. It's better to draw a horizontal line because there's no other vertical zeros while there is a 0 in that horizontal line. Now, to cover this 0, you could just draw a vertical line or a horizontal line. I'll go ahead and draw a vertical line here, a vertical line here, and a vertical line here. So now that is equal to 4 lines. All right, so just like that, you can figure out how many you need. All right, and if in this case this is equal to the number of rows, so what we do is we go to this one and we find a pattern of 0 such that each column and row has exactly 1 0. So the zeros that we are going to find, we can select any. It doesn't matter. There can be multiple solutions here. I'm going to select this one, this one, this one, and this one. All right, so you can see that this row here has 1 0, this column has 1 0 selected, this and this has 1, this and this has 1, this has 1. So I hope that's a bit more clear. All right, and now we assign it, so we find that and we go ahead and say that A should get basketball, B should get soccer, C should get tennis, and D should get cricket. That's how we apply it. Now imagine a scenario where that we had to go to the other one, all right? So an example for that is, so what you would do in that case, right? Imagine that we couldn't do it in the minimum, like the minimum number of lines was not equal to 4. All right, what we would do then is, just to give an example, is we would find the minimum uncovered number. So let me just draw these lines again, right? Find the minimum uncovered number, in this case 3. We subtract that number from all the uncovered numbers. So this one and this one is uncovered. So we go ahead and subtract it from them, and we are left with 0, 2, and 3, right? And we add that value to all the numbers that are crossed by 2 lines, which is this 0 here, this 4, and this 2. Okay, so we go ahead and add it to those numbers. Whoops. All right, so this becomes a 3, this becomes 4 plus 3, 7, and this becomes 0 plus 3, 3. All right, and then you would repeat that process and see how you go about it. All right, so that is the Hungarian algorithm. It is a bit long, but it is, at the end of the day, an algorithm. So as long as you understand what's happening and you're able to put those numbers in, you'll be fine. Now that works very well for a square matrix, right? Now imagine the case where the matrix is not a square matrix. All right, it's something like this, where it is the number of rows and columns are not equal. So let me just get this one up here. 55, 58, 61. All right, and you have 59, 67. 64, 60, 58, 52, 59, 58, 54, 53, 53, 49, 51, 48. So imagine you had something like this, right? And I have A, B, C, D, E, and I have V, W, X, Y. Okay? Imagine that was a scenario. So what we do is we add dummy rows or dummy columns, right? Basically 0 rows or 0 columns to make it equal. All right? So in this case, because there's more rows than columns, we would add in this column of zeros, and then we would go ahead and apply those steps again. All right, so following the Hungarian algorithm. So first of all, we find the minimum value in each row. It's going to be zeros all the time, so it's not going to change. Then we find the minimum value in each column and subtract that from all the values. So what we start getting is that the minimum value here is 55. Subtract that from all of them, you get 4 here, right? Sorry. Is that not a 55? That is a 55. Oh, sorry, that's a 56 here. So that should be a 1. Okay, you have 62. 55 takes 62 takes 55. That's 7. All right, this one is obviously becoming 0. All right, and then this becomes 3, and then you have 6. All right, now you go ahead and do that for all of them. I'm just going to skip through it really quickly. All right, so you get 1, 9, 6, 2, and 0, 0, 7, 6, 2, and 1, 5, 1, 3, 0, 2. Okay, so you go ahead and do that. Now you go to step 3. Okay, cover all the zeros in the minimum number of lines. All right, so to cover all the zeros, I think it's pretty obvious that we should go ahead and use this vertical line to cover all of these. Vertical line to cover this, vertical line to cover this, and a horizontal line to cover this, and a horizontal line to cover this. How many lines is that? 1, 2, 3, 4, and 5. Okay, amazing. So we go to step 5, where we find a pattern of zeros, so that each of the rows and columns have exactly 1. All right, so the zeros I'm going to select this one, this one, this one, this one, and this one. Okay, so now we know that C should get V. All right, E should get W, A should get X, D should get Y, and B, because it's pointing in something that's in the dummy column, it should not get it. Okay, it's not optimal to give him something that is that he needs. All right, something that he prefers. Okay, so for example, if you're trying to put people onto a team, right? For example, if you have a team of athletes and you're trying to find the best 4, all right, for each of their respective races, B should not get a place on the team because the others are doing a lot better for those races. So that's kind of how the Hamiltonian algorithm works for a non-square matrix, and that's it. I know it was long, I know it was tedious, I know it is tedious, but you have to get through it. All right, at the end of the day, it is very simple. All right, the hardest part is finding the minimum number of lines, but once you can do that, very chill. It's just applying an algorithm. So you just need to get some practice in and you'll be completely fine. You got this. Hey guys, 2 things. If you do have any questions regarding the content we just covered, just go ahead and drop that in the comments. I'll make sure to get to that as soon as possible. And secondly, if you liked the video or if you got anything that was useful from it, make sure to check out the website, Prep Folders. There's so many more videos like this, so many more resources, practice questions, and all the lot. So just go ahead and have a look. If you need help, there's some tutors and mentors there as well. So just have some fun over there. And yeah, we'll see you on the other side.